Today we are, last week we have summarized the properties, motivations, the method, especially the Alkire-Foster method, the adjusted headcount ratio, its partial indices. And when Anna taught, she had also gone through a little bit about subgroup decomposition, dimensional breakdown. In your assignment, you did compute M0 across subgroups and sensor headcount ratios. So in that sense, it's a class with recapitulating those concepts. And I will just give you some examples, given that you are working already in your with your data sets. So how you can use these ideas to analyze more, which will help you for your final presentations. So the main focus of this lecture, I will discuss two things in more detail. First, discuss how overall poverty can be decomposed across different population subgroups. And I will show some example of maps just for presentation purpose, but then Adriana will go through with some of the do files. Can you hear properly from the back? Perfect. And then Adriana will go through the do files and also show you how to create maps in Stata. So the first discussion is focused around the property, if you recall, population subgroup decomposability. Can anyone remind me what that property was about? Population subgroup decomposability? Right, go ahead please.
Like the total work is decomposable in the sum of each group.
Right, weighted by
Their share of each group.
the population share of each group. So the overall poverty, so if you know the poverty levels of different subgroups, then you can use the population share as a weight to sum them up to get the overall poverty. That's the main idea of population subgroup decomposability. And the second thing that we will discuss is how the overall poverty can be decomposed across different dimensions to understand the contribution of different dimensions, or deprivations among the poor in different dimensions. And it is related to the property of dimensional breakdown. Anyone remember what was the property of dimensional breakdown? Yes? No? Yes, go ahead please.
The share of the deprivation among the share of the indicators deprivation among
Close. So the main idea was, if you have an overall poverty measure and then you know the post identification, so you identify people as poor and non-poor, and then you look at post identification dimensional deprivation. In case of adjusted headcount ratio, do you remember something called censored headcount ratio? What was censored headcount ratio? Right. So censored headcount ratio was the proportion of population who are identified as poor and at the same time deprived in that particular dimension. Okay, so the uncensored headcount ratio was the share of the population deprived in an indicator irrespective of other dimensions. Censored headcount ratio, on the other hand, looks into the post-identification. That means it captures the joint distribution. It looks at the post-identification scenario. So for adjusted headcount ratio, just for example, adjusted headcount ratio, it can be expressed as a weighted average of the censored headcount ratios. Okay, so we will come to that just after some time. So that's related to dimensional breakdown. The main source of this lecture, if the book has been distributed to you, chapter 5 has been distributed to you quite a long time ago, and these two topics are discussed in section 5.5.2 and 5.5.3 of chapter 5. So recall this particular slide. You have seen this slide earlier. So the main idea is that you have subgroups, how the subgroups are created, mutually exclusive and exhaustive. Mutually exclusive means no one person can belong to two different groups, and exhaustive, that means it exhausts the entire population. It is not that some people are left out when you are creating the subgroups. And of course, by matrix X, we have denoted the achievement of the people, n people in d dimensions, where we denote the two subgroups. We just consider for simplicity two subgroups. It can be done with any number of subgroups, but just for two subgroups, we denote the achievement matrix of group 1 by x1 and that of group 2 by x2 with population sizes n1 and n2. And note that, of course, n is equal to n1 plus n2. So you can see these two groups here. So if you have the achievement matrix here where you have 3 dimensions and 3 people, then you may divide them in such a way that the first group, which is red here, contains 2 persons and the green group contains 1 person. Look, we have is exhaustive because we have exhausted the entire population, and of course it's mutually exclusive. Okay, there is no join between these two sets. And population subgroup decomposability is written by this. So if you know the poverty of subgroup 1 and poverty of subgroup 2 and their population share, you can always compute the overall poverty. This is actually quite strong if you are analyzing policy. It just allows you to look how different groups contributes to the overall poverty. Right? That's the main strength, the policy-oriented strength of this particular property. And then of course, one can calculate the contribution of each group to the overall poverty, which we just denoted by this notation, n1 over n, which is the population share, times px1 divided by px, poverty in subgroup 1 divided by overall poverty. So this is the share to overall poverty of group 1. Why it is important? You may look, say, the population distribution of within a country across different regions or social groups, and then just by side you present the contributions. The population share, when you do total 100%, and suppose you have 4 groups, 25%, 30%, 20%, and so on. So you have population of population share, and then you can present the contribution of each group to the overall poverty. Now, if you find that a particular group, even which has lower population, so lower population share, but has a really high share contribution to overall poverty, and of course you'll be able to identify that particular region. Look, this region, even with smaller fraction of population, has much higher poverty. So this is the main helpfulness, you should say, of this particular property. Let me go through with an example just to make it clear. I know many of you have already seen it and probably already know it, but let's go through with the example. So we just considered the following example, and this is what we saw on the first day. So you have an achievement matrix. Of course, in red color are those people who are identified as deprived in this indicator, not poor, but deprived in the respective indicators. You can understand that looking at the poverty line, respective deprivation cutoffs. So this is the deprivation cutoff for income, deprivation cutoff for education, and then so on. And the main idea was to dichotomize all these into 0 and 1. So if you are deprived, you get 1. If you are non-deprived, you get 0. Now suppose we have a weight vector. We just, to be consistent with the previous lecture, we just present the weight so that they sum up to the number of indicators. However, you can do the same exercise with weights that sum up to 1. Okay? But just to be consistent, we just use this particular weight vector, and then you get the G0 bar matrix, which Anna had introduced in her lecture. So you replace these deprivations by the corresponding weights. So income gets weight equal to 1, Then you have education gets weight equal to 2 and 2, and then for sanitation and access to electricity, they get weight of 0.5. Okay? Now, if k equal to 1.5, suppose somebody has decided, it's not I who am deciding, there is a dictator, God, whoever is that, has decided k equal to 1.5. Okay? So it's given to me. It is another question how you decide on k. That's a different issue, an empirical issue. Suppose we have a k which is 1.5. Who are poor here? Person 3 and 4. All three?
No, 2, 3, 4.
Ah, yeah, 2, 3, 4.
2, 3, 4. Yeah.
Okay, so all of them are. Yes, perfect. Perfect, very good. And what is the M0? How to compute M0? The adjusted headcount ratio? 3 out of 4. It's multidimensional. You need to differentiate between multidimensional headcount ratio and adjusted headcount ratio, right? Adjusted headcount ratio adjust the multidimensional headcount ratio with intensity. So you had the similar confusion some of you had in your exams, right? So there's a difference between adjusted headcount ratio and the multidimensional headcount ratio. Multidimensional headcount ratio is just an extension of the single dimensional concept of headcount ratio in the multidimensional context. That means it just asks what is the fraction of people that are poor. Adjusted headcount ratio, on the other hand, adjusts the multidimensional headcount ratio with intensities. So the multidimensional headcount ratio times the average intensity among the poor. Okay? Because so that it satisfies the dimensional monotonicity property. So the idea is that how you can compute M0, you just take the summation of all the elements and divide by the number of the elements. That means it's the average of all elements inside the matrix, right? So it's actually 15 over 32. If you sum them up, you will get 7.5 divided by 16. If you sum everything, 1 plus 1, 2, 4, 6, 7 and 7.5, 7.5 divided by 16, which is equal to 15 over 32. Very well. Now the idea is to divide this population into two groups, pink group and green group. You can call anyway, you can call gender as well. But anyway, we divide this into two groups. And you have done that, right, in your assignment already? You had divided them in two groups, and in your assignments earlier, you divided the entire matrix into two groups. Okay. So M0 for the pink group, if you sum everything up, is 1.5 over 8, right? So it's 3 over 16. And M0 for the green group is 6 over 8 is equal to 3 over 4. The overall M0, it can be easily computed by the population share, which is half, right, in this case, times 3 over 16 plus half times 3 over 4 is 15 over 32. So whenever you compute, when you are doing subgroup analysis, you can always check that this particular relation holds. We do all the time in order to just to avoid that we did not have any problem in our M0 computation. Okay, so we always do this kind of cross checks so that we understand, and we find mistakes honestly. Sometimes they sum up to 1, so we understand there's some mistake has gone inside our computations. So this is a nice way to cross check when you have all the figures. Very well. So now let's now look at the contribution. How do you compute the contribution? So of course you can see the population share, the 50%, right? The population share of the pink group and the green group to overall population, the 50%. 2 out of 4, 2 out of 4. Agree? What is the contribution of a particular group to the overall poverty? This is how you compute. You take the population share times the M0 of that pink group divided by the overall M0. So get 1/5, and contribution of the green group, which is group 2, is 4/5. So although the population share is just half and half, By looking at the contribution, you can see with same population share how one group is contributing more to the overall poverty than another group. So when you are doing the analysis, when you are doing the country analysis, you are going to present the results that you will do this Friday. You can always try and see how the contribution of these different groups to overall poverty, they are in comparison to their overall population share. So if you have, suppose if you have one column where you have the population share, and the next column you report the contribution of a group to overall poverty, and you get identical result, what does it mean? Suppose you have identical elements in these two columns. One column has population share of different groups, and the other column has contribution of each group to overall poverty. And suppose you get identical elements in these two groups. What does it mean? What would you infer from that? May not be wrong if you get that identical situation. It is possible that disparity in poverty is not large across groups. Okay, actually there is no disparity. All groups have equal poverty. Okay, they are going with their population share. Of course, you have to go inside, look at intensity, incidence. That's something later. But if you look at the overall poverty, you just see geographically there is no disparity in overall poverty. But if you have big discrepancies, of course, then there is big disparity in poverty. And of course, make sure that the contribution must sum up to 1. Again, that's a cross check. You do all your calculations and then go through this cross check. This is another cross check. Now, how does it help to analyze? So this is Nigeria, whose MPI is 0.240, okay, based on our new results. What do we do? When we go inside, what do we see? This is what we see. Quite wide disparity within or between subnational regions. I will come Wednesday and talk about inequality, and there we will talk about within and between group inequalities. But you could see a huge amount of disparity in Nigeria. So if you try to compute the population share, also the contribution, you will see these regions would have much larger contribution to the overall poverty, right? So actually subnational MPIs range between 0.045 to 6. Look at the average and look at the disparity across regions. It's huge. Now you could do that. I mean, you could do that with a non-decomposable measure as well. Not necessarily all measures, they are subgroup decomposable. But the problem is that they won't add up to the overall poverty figure. That is what the subgroup decomposability property provides. You could not even compute the contribution if it is not subgroup decomposable. Okay, you just get this particular map of regions and you stop. You cannot go ahead if you do not have a decomposable measure. That's where the value added of decomposability comes into place. Similarly, if you look at India, same thing. This MPI is 0.283, but then it ranges between 0.051 and 0.6. Now, I had done a work with Sabina where we tried to see how multidimensional poverty went down between 1999 and 2006 in India across these two periods. And when we studied, look at the national level, fine, there was national reduction and the rate was actually faster than the rate of income poverty reduction. When we look at within the country, we found that these were the poorer states to begin with, and their progress has been much slower as well. So these were the states to begin with, much poorer, and they did not make significant progress. Their progress was also slower. It was very unlike the income poverty reduction actually. In income poverty reduction, we found larger states made larger progress, at least in terms of absolute reduction in poverty. In terms of multidimensional poverty, they did not. Okay, again, you can decompose the overall change to see which state has contributed more. You can decompose by population effect and poverty effect, different kind of things, because you had migration between these regions as well. Now we can only do that when our poverty measure is decomposable, otherwise it's not possible. Similarly, this goes really fast. Similarly, we also look at other population subgroups, and also we found, actually it was a consistent finding, that the poorest subgroup had slowest reduction in multidimensional poverty. We also did certain different things. We looked at national disparity within each regions: Latin America, Caribbean, East Asia, Pacific, South Asia, Sub-Saharan Africa, then low-income countries, middle-income countries. When we look at the disparity across subnational regions, they are much more widespread. Look at here. It was only one country which had no country actually among lower middle income countries had MPI even larger than 0.5. Now when we break it down across subgroups, you see there are way many regions which actually had much larger poverty than that. And this is the kind of map we did, global map in 2011. We have not replicated, we have a different kind of maps now. But just to give you a flavor, so we had the national MPIs, and then what we did, we tried to find out, and this is sort of the regional decomposition that you get after you plot inside the map. If you look at a particular region, say Sub-Saharan Africa, very closely, you can see there is wide disparity that should be captured and has captured and sort of decomposed using this measure. Now, the objective of this lecture was not supposed to be very long, because you already know, just to give you some ideas. Now, here are some set of questions. Okay, let's see if we are already clear about these questions. So the first one: what is the difference between the raw headcount ratio, which is uncensored headcount ratio? We used to call it raw, and I have not changed it, forgive me. Uncensored headcount ratio and the censored headcount ratio. What is the difference? I already mentioned at the beginning of the class. If anyone could clarify. Yes, please.
So uncensored, we're focusing on the whole society, whole population, and censored on the poor.
Anything else? What is uncensored headcount ratio? What is the definition of uncensored headcount ratio?
It's the headcount ratio of the entire population.
Uncensored headcount ratio for particular dimension. Okay? Yes, please. Irrespective of other dimensions. That's the thing. So it's not dependent on other. And the censored headcount ratio? You have a cutoff point. So the percentage of population who are multidimensionally poor and deprived in that dimension. So there is a post-identification criteria. Second question: can the raw headcount ratio of a dimension be lower than its censored headcount ratio? Again, please read the raw as uncensored. So can the uncensored headcount ratio of a dimension be lower than its censored headcount ratio? How many of you would say yes? Please raise your hand. How many of you would say no confidently? Good, at least more. And why is that?
The denominator is always high in the first case.
Because denominator is same. Denominator is same out of the entire population, proportion of population. Denominator is same. There is no change. Is the numerator, because in the numerator for uncensored headcount ratio, you have those who are deprived in that, irrespective of other dimensions. Now, when you are applying the censored one, denominator is same, but in the numerator, you do not have all the deprivations, only the deprivations faced by the poor. So you are ignoring some of the deprivations if those people are identified as non-poor. Is that clear? Please raise your hand if it is not clear. I will explain again. Okay, then I have to ask randomly any of you. Please explain. Anyway, I'm kidding. Question 3, can the censored headcount ratio of a dimension be higher than the multidimensional headcount ratio, not adjusted headcount ratio, multidimensional headcount ratio? Can the censored headcount ratio of a dimension be higher than the multidimensional headcount ratio? Please raise your hand who thinks yes. Could you please explain why?
Because after that we have to multiply by the 8. No, by the 8, and
Who are you multiplying by H? I'm talking about multidimensional headcount ratio. It's H.
the summarize of the height. We have to get the summarize. No.
So the multidimensional headcount ratio means the proportion of the population who are poor. Suppose you have 50% of your population as poor. The sensor headcount ratio is the proportion of the population that are multidimensionally poor. That means those 50% and deprived in that dimension. So it is not possible that deprivation in that dimension is larger than the number of poor. As a result, when you are talking about the sensor headcount ratio by definition is the proportion of the population that are multidimensionally poor and deprived in that dimension. So it is not possible that if you are focusing, you are restricting the number of multidimensionally poor, the deprivation goes up. It is not possible. There is an AND operator. 50% and those who are deprived. It cannot be more than 50%. Okay? If you had said 50% of the poor or deprived, that would have been different. But when you are using AND, it can never be. So, sensor headcount ratio of a dimension can never be higher than the multidimensional headcount ratio. Sorry? Yes. It can even be equal. So, it is equal. So, when I am saying no larger, that means it is equal or lower. Yes, of course it holds. Because it is possible, if you think about it, suppose you have 50% of the population poor. It is possible, suppose take the water. It is possible that some of the poor are not deprived in the water indicator. So it is possible that you take the 50% and out of those 50%, probably 40% are deprived in water. Okay? This is how the equivalence holds. Good. Is it clear? Please raise your hand if it is not clear. I will explain again. Perfect. Thank you so much. I like the courage. Very good. So, do you understand what is multidimensional headcount ratio? Perfect. So, you have 50% of the population. So, you have the matrix, and this 50% of the population identified as poor, 50% as non-poor. The sensor headcount ratio is a percentage of population who are multidimensionally poor and deprived at the same dimension. So, suppose for water, 50% of this population poor, and of those 50%, 40% is deprived. Okay? So, then sensor headcount ratio is those deprivations divided by the entire population. That's a sensor headcount ratio.
So in that sense, you have to qualify the dimension. Don't say sensor headcount ratio, say sensor headcount ratio for particular dimension.
Exactly. So, sensor headcount ratio of a dimension, uncensored headcount ratio of a dimension. Definitely. Then question 4, what is the relationship between sensor headcount ratios? Yes?
Have you ever come across an empirical result where the multi-dimensional headcount ratio is equal to the sensor headcount ratio?
Very unlikely. Cooking fuel is the dimension where it may be possible, because in some countries the cooking fuel deprivation is almost 80%, 85%. So, although we have not found exact same figure, Adriana could rectify me if she is here, but I don't think we had a sensor headcount ratio which is equal to the multidimensional headcount ratio. But for cooking fuel and sanitation, they were close. Did we have any country where we had the multidimensional headcount ratio exactly equal to the sensor headcount ratio of a dimension?
Well, the unsensor is equal to the
No. The multidimensional headcount ratio. So that means all poor are deprived in a particular dimension. Adriana has. I mean, empirically we have not seen close. I mean, if we look at in the case of India, I have worked. It's very close. 90% of the poor were deprived in cooking fuel. But we have not come across a situation empirically where they are exactly equal. I mean, it is possible you might say that they are so close that you cannot statistically distinguish between the two. It is possible, but we have not found exact equal. Yes.
How do you, maybe it's basic, but when you first asked the question, I thought that we could find a censored headcount ratio of one dimension that could be higher than the average multidimensional. Because in
What do you mean average
like
multidimensional?
the multidimensional headcount ratio, you are saying that it's in one particular dimension.
No, multidimensional headcount ratio is not a particular dimension. Multidimensional headcount ratio
No,
is
but poor, but also deprived in one particular dimension. That's
multidimensional headcount ratio is the proportion of population multidimensionally poor. That's it. It does not belong to a dimension. It's the overall. What if I ask you what fraction of the population in your country is poor? Poor, not deprived. Your answer would be suppose 50%. That means they are poor. So it does not relate to any particular dimension. The adjusted headcount ratio is multidimensional headcount ratio by times the average deprivation square among the poor. Make sense? So the uncensored headcount ratios or raw headcount ratios belong to each dimension. So if you have 10 dimensions, you have 10 raw headcount ratios, uncensored headcount ratios, 10 censored headcount ratio, but multidimensional headcount ratio is 1 for a particular k. If you vary your k, it can change, but it does not belong to a dimension, particular dimension. Yes, please.
I was expecting to hear union and intersection methods, when you talk of.
Yes, please go ahead. Ask your question. Yes, go ahead.
Yes, I wanted to hear you saying, well, like, when you use a union method and an intersection method, this is how the multidimensional
Perfect.
headcount ratio will change.
I come back to it. I mean, I have a slide where I will talk, but let me come back to it. But good question. Thank you. Then, what is the relationship between censored headcount ratios, that means all censored headcount ratios, and the adjusted headcount ratio? You have seen that relationship. No? Yes, please?
Sum of the weighted headcount ratio.
Right. So, M0, adjusted headcount ratio, is equal to the weighted average, which means you use the weight of each dimension times the censored headcount ratio and you add them up. So, it's a weighted sum of the censored headcount ratios, which gives you the multidimensional headcount ratio. It makes your life easier to decompose or find the contribution. And then, of course, the question is what kind of policy analysis can be conducted using the censored headcount ratios. What censored headcount ratios tell you is that the level of deprivations among the poor. Okay, so when you find a contribution, of course, they depends on weight. Suppose you have an equal weight case, then also you look at the overall poverty and you find the contributions. You see some of them probably is contributing say 20 to 25%, some of them are contributing only 3 or 4%. That shows you the composition of the overall poverty across different dimensions or indicators. Let's see, let's go through and see, and please feel free to stop me and ask questions if you need clarification. So again, we start with an achievement matrix where we have the achievement of each person in each dimension. In this case, we have 4 persons and 4 dimensions, and then we have the deprivation cutoffs, 4 deprivation cutoff. And this is how we get the previous slide needs updating. But anyway, then you compute then you identify the deprivations of each individual in each dimension. What is the uncensored headcount ratio for each of the 4 dimensions? You have already computed uncensored headcount ratio. So uncensored headcount ratio is the proportion of the population deprived in a particular dimension irrespective of deprivations in other dimensions. So what fraction of population is deprived in the first dimension? 50%. So the uncensored headcount ratio of the income dimension is 0.5, 2/4. Similarly, what is the uncensored headcount ratio of sanitation? Of sanitation? 1/4. Perfect. So those are the uncensored headcount ratios, and you have already computed them in your assignment initially. Okay, so the uncensored headcount ratios. So if you have a stata data set, can anybody tell me if you are given the deprivation, say 0, 1 vector, what command would you use to compute the uncensored headcount ratio of a particular dimension? Sum, and then you, of course, with using the sampling weight, and then you capture the mean. and that gives you your uncensored head count ratio. Perfect. Now suppose you have the weight vector as we had in our other examples, and we get the weighted deprivation status value matrix, from which these weights are given by Wj, and we compute the deprivation score vector as this. This is you have already done, you have already computed while doing M0. Now suppose k equal to 2. How many people are poor? 2 of them are identified as poor. Now we censor the deprivation matrix and the vector, and this is how you do. You replace the elements of the non-poor person by 0 because you just censor them. This is the censored matrix. Look, we did not have a k here. We are adding a k here in this place because depending on the cutoff, you are just censoring the entire matrix. So M0 is 6/16, which is easy to compute. There are 4 dimensions denoted by this D 1, 2, 3, 4. So D equal to 4. So now instead of grouping them across the population, you are grouping them across dimensions. What is the censored head count ratio of each dimension? Louder, please. For income, 1/4, education, half, and then 1/4 and 1/4. Perfect. So this is how you compute. So when you are computing in stata the censored head count ratio, you need to create a variable which says if the uncensored, if they are deprived in the dimension and they are poor, and then you get a 0, 1 variable, that then the mean of that 0, 1 variable will give you the censored head count ratios. Okay? Perfect. Now uncensored versus censored head count ratio. The uncensored head count ratio of a dimension denotes the proportion of population deprived in a dimension, right? And the censored head count ratio of a dimension denotes the proportion of the population that is multidimensionally poor and deprived in that dimension at the same time. So it has to hold together. M0 and censored head count ratio. If the censored head count ratio of any dimension j is denoted by Hj, it should actually be Hjk in, please read it as Hj and k in the bracket. Revise it. This Hj is just uncensored head count ratio. Then the M0 can be expressed as, these are the weights, okay, the normalized weights, you divide by d, you get the normalized weight, times the uncensored head count ratio when you sum over all d, okay, and then it gives you, so after you have computed the censored head count ratios, you know the weights, then you can always check if they are summing up to M0, as you had done in the assignment, another kind of check to make sure that your results are right, results are okay. And the contribution can be computed, again there should be a k here. The contribution is the normalized weight times the censored head count ratio divided by the overall M0. This is the contribution of this particular. So the contribution is not only affected by the censored head count ratio, also by the weight attached to it, because the weight plays a role here. Now M0 and uncensored head count ratio. Thanks for the question at the beginning. What is the relationship between uncensored for the union approach? So when you have a union approach, what is the relationship between first the uncensored head count ratio and the censored head count ratio? For union approach, what is? They are the same. So when in the union approach you identify everybody with at least one deprivation as poor. As a result, there is no censoring taking place actually, and consequently your censored head count ratio of a dimension is equal to its uncensored head count ratio. So for union approach, what is the relationship between M0 and uncensored head count ratios? The relationship between the adjusted head count ratio and the uncensored head count ratios for the union approach. Sorry? Yes, so The M0 in this case is just the weighted average of the dimensional head count ratios. Okay, so it can be actually calculated even without considering the joint distribution. So you compute the uncensored head count ratio for each dimension and just take a weighted average, you get the M0 in this case. So even if you do not know in this case the joint distribution, it is possible to compute and it becomes sort of a composite index. Okay. So for union approach, the censored head count ratio of a dimension is equal to its raw head count ratio, and so M0 in the union approach is the weighted average. So you get your answer. So for union approach, this is what you get, and rest of them are covered through censored head count ratio. Even if you go to intersection approach, note tell me for the intersection approach, what is the relationship between the adjusted head count ratio and the multidimensional head count ratio? For an intersection approach, what is an intersection approach? Sorry, louder please. All. So what is the relationship between the adjusted head count ratio and the multidimensional head count ratio? You know from the relationship M0 is equal to H times A. Now what is A for intersection approach? 1, because intersection only identifies those who are deprived in all dimensions simultaneously. So they are deprived in 100% of indicators. So if you take the average, you get 100% or 1. So A is equal to 1, which means M0 is equal to H. So the adjusted head count ratio is equal to the multidimensional head count ratio when you have the intersection approach. And what about the censored head count ratios in this case? What is the relationship between the censored head count ratio of a dimension and the multidimensional head count ratio? Those who are poor, they are all deprived in each dimension, right? So the censored head count ratio is also equal to the multidimensional head count ratio. So if you identify 10% of the population as poor using your intersection approach, that means this 10% of the population is deprived in all indicators. So if you need to now find the proportion of the population that is multidimensionally poor and deprived in a particular indicator, that's also 10%. So when you have an intersection approach, your censored head count ratio of each dimension is equal to the multidimensional head count ratio, which is equal to the adjusted head count ratio. So these are the relationships that hold, that equivalence that hold in this case. So what is the contribution of the education dimension to overall M0? A small example, let's compute by our head. What is the weight attached to the education dimension, or the relative weight attached to education dimension? Relative weight 2/4, so half. What is the censored head count ratio? Half. And what is the M0? 6/16. Perfect. So you have half times half divided by 6/16. You get 2/3. So in this case, the contribution of the education dimension is 2/3. Now, if you had equal weight, instead of this unequal weight, suppose you have equal weight, what would have been the contribution of the education dimension? If you would have equal weight, suppose you have 1, 1, 1, 1, equal weight across all 4 dimensions, what would have been the contribution of education dimension then? Given that you have the same censored deprivation matrix, because note identification might change in that case, but if you had the same censored deprivation matrix, it would have been 2/6 actually, 1/3. Okay. Now what we can do and how we have used the censored head count ratios and its relation to M0 for our analysis. So here you have example of 3 different subnational regions from 3 different countries which had very similar MPI, and you have this example in the book chapter as well, but a very different composition of across these different. So weights are same across indicators in all these 3 countries, but you could see that it's quite different contribution across these different indicators. So it actually tells you which dimension probably requires more attention immediately in that particular country. Here is an example where you have very different MPI, but you had similar compositions. So those were the things we did initially at 2010. So these are figures from 2011 data. Another way of representing, and we look forward to see different kind of representations from you on Friday. So this is a spider diagram that also shows here. You have, if you look at on the top, you have a very different level of MPI, but similar sort of dimensional composition. Here, on the other hand, you have a very same MPI, but quite different composition, but it's another way of representing, understanding whatever makes you feel good. I mean, the main difference is that in the other figure, it is really difficult to know the level of sensor headcount ratio because you just look at the contribution. Okay? Here, on the other hand, these spider diagrams can be understood easily because you can also see the rate of the sensor headcount ratio, the level. Again, it's similar thing, and it is from Sabina and Mariama's paper trying to understand different type of compositions. So Zambia is more deprived in living standard. Nigeria is more deprived in health and education, and is most deprived in education, much larger. And this is an example from different states where you can see that if we look at Kerala and Delhi, although one is city and another is other state, but still, just to show you the difference in composition is quite different, although they had similar levels of MPI. And similarly, as you had looked to the decomposition across, now what we are trying to do, we are trying to merge these 2 concepts of decomposition across population subgroups and composition across dimensions. Then you can present different maps across these different sensor headcount ratios, and not necessarily different regions rank equally. So when you compare these different maps side by side, it is possible for you to point out graphically which regions are suffering more on which particular indicators. Similarly, it is for South Asian regions, and here are some graphs. So I hope you will be able to generate some of these graphs by Friday using Stata Command for your particular countries. So I will stop here, and then I will leave Adriana to go through some of the Stata files and how to create maps. Now, before we proceed, do you have any question on the different relationship? I hope the relationship between these different partial indices, they are clearer now.